Hello, everyone. Thanks for being here to listen our topic. I'm Minrui Yan, and he is my coworker, Jiahao Li. We are from the same team called the SkyGo team. I'm very glad to be here. Today, we will talk about our methodology about how to control connected vehicle remotely. In this talk, we will introduce our team and what we have done first. Then talk about what is telematics, what inside and how it works. At the attack surface section, we will talk about security risks and vulnerabilities of software and hardware in telematics. Finally, we will use some case to show what we have done, how we can control vehicle remotely and execute some orders. Who we are? We from SkyGo team as vehicle security team, focus on vehicle security research and evaluation and defense. In these years, we have some research about the vehicle security. Tesla Model S hacked to start without key in 2014. Remote control vehicle via telematics in 2015. And can you trust autonomous vehicle in 2016? This is an attack on Tesla's autopilot system. And CAMPIC is a tool for evaluating CAN bus in 2017. Attack surface for connected vehicle in 2017. And we also have some security products such as CAMPIC and vehicle guide and in-vehicle network defense and security development kit. And these are our clients and partners. Okay, let's have a look at what is connected vehicle. So what is connected vehicle? In short, covers telematics. So what is telematics? Telematics is a term that combines word telecommunications and informatics. It has a lot of functions. This technology is used in our daily life, including taxi, express, vehicle checking, and even remote control. So maybe you buy some new car, you can control your car, use your phone, open the door remotely and start engine. This is a simple image to show what is telematics. There are several key points in this image. The first key point in telematics is IVI. So what is IVI? IVI stands for in-vehicle infotainment system. It's always a bigger screen in your car, and you can use it to navigate, control the vehicle, monitor the car state. In some modern cars, IVI also can send and receive CAN bus message. Because if you wanna control a car, such as open trunk and open door, you can use your IVI to just click the screen, and the IVI will send the CAN message to in-vehicle network. Then the door will open. So IVI operation system includes Android, QNX, WinCE, and other things. Most of them are Android systems. So it means they may have lots of vulnerabilities. And by the way, in different countries and regions, IVI has different names, such as HU, DA, or CID. HU means head unit. It's almost widely known. DA, display audio. We see this term in Japanese car. And CID for Tesla. The second key point is TSP. TSP could store your user data and analyze them for providing service. So, so that they may have your sensitive data, like your driving path. They could know where you went last night. In some cases, you could install an application in your smartphone and use it to get your car's status and control your car remotely. It's a lot of cloud service. The next key point is telematics box. The telematics box is a key point in telematics system because it connects in-vehicle network and the external network. If T-box is compromised, attacks could connect to in-vehicle network, and the car will under the control of the attacks. So the attack could use T-box to send some CAN bus message, and he could control car. The T-box is somewhere in the car. It supports for data collection and help you control the car remotely. It also has the anti-theft function by monitoring the car's status. T-box can send CAN bus message to the car, help you to open the door, start the engine remotely. Basically, T-box share internet access to IVI. So T-box is the critical point in telematics. After understanding the role of this device, let's talk about how they link with each other. This image is a map of an in-vehicle network. This block represents ECU. Different mode of cars has different in-vehicle network maps. This image is just a simple map. The real in-vehicle network is more complicated than this one. There are some different bus in a vehicle, such as CAN bus, LIN, Ethernet, FlexRail, most. The network connect ECUs. If you like to monitor your car, you must know what is ECU turning. However, ECUs we talk about today do not include engine control unit. In vehicle network, gateway mainly functions are isolate different networks and forward data. Body control module control the door, seats, roofs, track, and some other things. And the head unit is in different network with BCM. If you want to open the door remotely, one thing you need to do is using the application in your phone. It will send a command to TSP. Then TSP will generate a command to T-box. Then T-box will generate a CAN bus message to CAN bus. At last, ECUs will follow this CAN bus message and execute the command to open the door. So how to start a research? If you want to start your vehicle research, you may have a question: could I damage the car? Of course, if you don't afraid of doing damage in your car, but sometimes we don't have to do the research in a new car. All you need is a simulation environment. I will give you some advice. To build a simulation environment, we need to have some parts from a real car. You can buy car parts on eBay or Alibaba and Taobao. It's very cheap. This is the plan A you can buy from the online market. The plan B is out parts market, is offline. The better choice is auto parts market offline. They have different car from the world, and they take them apart and sell the parts. In China, we can buy almost any part from the market, and the price is much cheaper than replacement parts sold in 4S shop. We need to prepare these tools to disassemble cars part and PCB, such as state-safe tweezers, digital multimeter, cutter, stripper tools, soldering station, pre-tool, and so on. These tools will spend about 1,000 bucks. To build a simulation environment, sometimes we need to connect some information from a real car. By doing this, we can find out where are the devices and how they link with each other and how they work. To make sure parts can run outside of the car, we need to know what is operating conditions for the parts. This could be some signals from different ECU. The most important thing is enable signals. The most important enable signal is CAN bus message. So we need to use digital multimeter to find out which connector is connected to the CAN bus. Then we can use CAN bus transceiver to record CAN bus message. CAN message can be pre-dialed and pre-dialed message or checked message. The message can keep the ECU running individuals. The checked message could wake up or shut down the ECU. This is a chart of CAN message. So you have to record the CAN message before you start engine, and you record for a while, and then you start engine, and also and then record other data packet and diff them. So maybe you can find some different. That is the result you need. Connector ECUs according to the real car. Supply the DC power, then you need to keep sending enable signal that you find from the real car. In this figure, we used STM32 to send the CAN bus message to T-box. This is a wake up command in CAN bus message. This is a very simple case. In other complicated case, more ECUs are required. Okay, let's talk about attack surface. Jiahao Li will take over from here.
All right. To find the attack surfaces for connected car, you should collect the PCB components information, including the processor, flash IC, interfaces. Then you can analyze the architecture so that you are able to know which IC is wrong. And finally, we can analyze vulnerabilities from the dumped firmware. We mainly focus on the T-box, the RVI, and the TSP. I draw several diagrams of their architecture. Let's take a look. What is in the T-box and what they can do. Usually, the MCU connects to the SoC via serial port. The SoC stands for system on chip, and the serial port is UART or GPIO. And they all connected with an Ethernet switch. The T-box connects to RVI via USB. This is USB port. And the MCU sends CAN messages by a CAN transceiver. Then the FOTA program runs on the SoC. and it's able to upgrade the MCU and RVI. As an embedded device, it also has some debug port for flashing firmware and on-chip debugging. And it always has a system such as Linux, Light, Android. You can find it in a flash memory chip. At left, this is a eSIM, embedded SIM card. We can identify the chip by the packaging. To use the eSIM of T-Boss, we need to prepare the LTE modem device. It can be an unlocked 4G Wi-Fi dongle, or a 4G IoT module, or a mobile phone with SIM card slot. But until then, you need to get the right APN configurations. So what's the APN? APN stands for access point name. It is the name of the gateway. Internet service provider could set a different APN for different network situation. Some sensitive devices using the 4G module combined with APN make the network convenient, safe, and reliable, such as ATM, POS, and telematics. TSP connect to the vehicles via the MSTP list line. The MSTP list line you can see in this picture is GRE tunnel. So we can use it to connect to the automaker's internet and find something interesting. The TSP is worth to attack because it has many essential services. It is related to the network of suppliers and automakers, and penetrating is easier for a security researcher. For the App Store, the App Store is the left. For the App Store, we can put an app with a backdoor. For the user center, we can get privacy information of users, include the car app token, so you can request the API to control car with this token. For the firmware over-the-air server, FOTA, we can penetrate it and put malicious upgrade packages on it. Only if we hijack the remote service, we can control car remotely. And if we attack the supplier's network, we can scale our attack. In other words, if suppliers provide services for automaker A and automaker B, you can control both vehicles of the automakers. And we have done that. You might think it's not easier to access the internet. There are firewalls, IPS, IDS, and WAF, but I tell you, it's possible. We found a way to access the internet by a T-Boss which has APN configurations, and it's difficult to trace back attack source. This is the architecture of RVI. The inside of RVI has divided two parts. The operating system runs on MCU of core board. This is core board. And the eMMC usually contains operating system. The display managed by MPU, and the power managed by MCU on the button board. And the MPU connect to the MCU, usually with a PCB connector. It composed of some interfaces, such as UART, SDIO, I = C, and theta, and so on. The MCU send CAN messages also by a CAN transceiver. This is a transceiver. Okay, for common RVI, we can plug a USB Ethernet dongle into the media port of RVI, and the embedded system maybe not verify the VID, vendor ID, and the product ID of the USB device. They call VRD and PRD. Thanks to the Linux default drivers, the IVI system can recognize the USB device as ETH0. The default network configuration results in that it assigns a static IP address or obtain an IP address from DHCP. So we can scan the IVI network services in WLAN or wired Ethernet. The ADBD or SSHD, usually without authentication, and we can get a shell easily. On the other side, the IVI suppliers may keep a hidden entry on system UI. Only touch the edge of screen regularly. Touch, for example, touch up, up, down, down, left, right, BA. So you can get a shell. For some IVI, you can get a shell by this trick. Then we need to plug a keyboard or mouse to input a command on the terminal. On the PCB board, like this, on the PCB board, there are perhaps a UART port on the side of SoC. A TTY console runs on this port. You can use the USB serial adapter to access the debug shell. It's by that we can also read the memory when it's running. The device in this picture is USBDM freescale, and refresh malicious firmware instead. If you want to add a backdoor, you can do it. This is the USB port you can see in this diagram. Usually, the T-Box connect to IVI as a Randis device, and the IVI connect to the internet via T-Box. The PID and the VRD are private possibly. So here are two ways to attack the structure. For the IVI, we can customize an embedded device with a custom VRD and PRD in USB whitelist, such as smartphone or Raspberry Pi. So the IVI can recognize the malicious USB device as a Randis device. For the T-Box, we can modify the drivers to apply the T-Box. Then we can control the T-Box via ADB or SSH. And we can penetrate the TSP via T-Box network. The automotive USB connector is usually not the USB standard. Perhaps it's a round shape HSD connector or a square heteros connector, so you can make it work by jumping wires to USB type B cable in this picture. The port in red looks like an HSD interface, but actually it's a USB interface. We only need to make a cable USB to HSD and connect to our computer. Use the ADB command, then we will connect to the T-Box and get root privilege. You need to analyze the system file to find more vulnerabilities. If you don't get a debug shell directly, you could dump the firmware by programmers or card reader. At the left, the picture mainly shows flash ROM programmers. At the right, the photo shows the microcontroller programmers. These tools are cheap and suitable for most chips. Here is a reading from SD card. Reading files from SD card is amazing. This board is Tesla, and we found 2 SD cards on it. In left SD card, I found many CUs firmware, showing the right image you can see. A little harder if we get a locked card. A logic analyzer is a great tool. We are able to sniff the password from the communication between SD card and the host. In this graph, the password transmitted on the data channel 0, you see this green. So we pass the password data from the logic analyzer, patching the SD card driver in Raspberry Pi system. When inserting a locked SD card, it can be unlocked automatically. So we can mount this partition successfully, and we can read the file. It's common that automaker put firmware into flash ROM. The flash ROM stores important data, while dumping the firmware from flash ROM is the first stage. Checking the brands, and data code on the IC. And then we can Google write data sheets on the IC. According to the pin assignments, we can know what protocol did you use and know what its useful is. Boot ROM, operating system, or cache. And we can use the right programmer to dump the firmware. The Tesla runs the Linux on NVIDIA core board. We take off the eMMC by a BJ rework station. Use small words, the BJ rework station is a super hot air gun. After you dump the firmware by the programmer, reboarding the IC, so we can fix it and make it working again. So we needn't to purchase a second Tesla CRD. This picture shows Tesla eMMC files we extracted. And write the root hash in the shadow file, and there are browser dynamic library in other directory. It's a WebKit kernel. You can debug the browser kernel on your simulator. The NAND flash program is a little expensive. For example, the PC 3000 flash program is about $3,000, and it may be not compatible with some NAND flash. You can replace it with an evolution board, such as a Raspberry Pi, Arduino, STM32. By jumping wires to the GPIO, we can read the blocks of NAND flash. There are also some differences between different firmware. It's too complicated to talk about. Let me just mention to you the common analyzing methods. You should extract the firmware first. If you don't know what the firmware is, use the bin work or strings. If you know the firmware contains partitions, you can use mount commands and DD command or NAND simulator driver to mount a UBI file system. Then you can reverse engineering programs or bootloaders by these common tools. You may ask, how did you know which to analyze? If you know about embedded development, you must know the system driver is the key. So we can analyze the program, how to driver the MCU. By the way, we can find the TSP configurations, use TSP dump to capture data. If the data is encrypted, you can reverse the cipher algorithm. According to the architecture and the attack surfaces aforementioned, we are able to hack a real car. Here are 4 real cases, and the sensitive information has been removed. There is another way to get APN configuration. We can sniff the UART communication between MCU and the LTE module. Then the AT command printed on the console. It contains an APN configuration. We can jump wires from an eSIM to a phone SIM card slot, then configuring the APN on the mobile phone. In this case, there is a chip made by Freescale. We found the debug port which is not disabled. Then we need a more professional tool to dump the firmware. We can also get the APN from the MCU firmware. It's plain text in red, you can see. In this image, we could find some services is running and listening in 0.0.0. As previously mentioned, all devices in the same intranet, not internet, intranet. It means you have access to connect their services via APN. In other words, you can attack other T-boxes in the same intranet. By finding the configuration files, we could know some sensitive information about API or other things. In this case, I got lots of administrator dashboard and foundational services such as Zabbix and GitLab. It's easier for web guys to do something interesting. So you know how to access the automaker's intranet in a different way. Then I will show you the case 2 TSP. First, we jump the wire to the eSIM. After setting the APN, we can access the intranet. You can see the delay time is not bad. So we can scan the intranet by eSIM. Finally, we got root privileges of vehicle gateway server by long time penetration, and we found terrible things. The key pairs, they stored the key pairs in the server. They did it for convenience, but it's insecurity. We can log in mostly Linux server of this resource group. Also, the key servers are in the intranet. There are proxy servers between vehicle gateway and the T-box. We found the command server finally. More lucky, the communication methods between vehicle gateway and the command server is HTTP, and its payload is plain text, so we can analyze it easily. We send a command to our car, then capture the corresponding payloads by Wireshark. And we found all the command names. The command server sends commands to vehicle gateway with tokens. The tokens are the operation ID and the CMD ID. We call it command ID. In this picture, you can see CMD ID in right window. The operation ID is fixed by specific car versions. The command ID is the real token generated by data center. We wrote a script to control car. The method send is to compose commands for controlling a car. It sends parameters including VIN, operation type, operation content, command tokens, and the timestamp. But it's not always success as we expected. We found that it would success only if we have sent a command by an official mobile application before. Finally, we found that the T-box will sleep automatically, and we need to send a wake up command to the T-box at first. The wake up server provides an API. The payload format is similar with the previous. The most important parameter is the phone number, and the parameter app key, sign, token is for the third-party SMS API. So you know, the wake up command is based on SMS. And you can wake up a T-box by your phone, but you had better not to hack in with your chassis. By the way, a connected car can also be controlled by SMS. It seems like a live chat. You open the door, and then the T-box replied, the door is opened. You may think it is ridiculous, but this bad design is really existent. You may not understand the control procedure. Don't worry. I draw a simple flowchart. The proxy servers and the internet service provider tunnel are omitted. The controlling server also omitted. All you need to focus is the gateway and the wake-up server. The mobile application sends the control command to application backend server. Then the backend server requests the command to TSP gateway. You can see the step 1 on this chart, request phone number. TSP gateway will request the phone number from data center. The data center is not the same database server, it's macro coped services. Next step, TSP gateway will send a wake up command to wake up server with tbus M2M phone number parameter. Then the tbus will wake up and connect to the TSP gateway and register services in step 4. Then the TSP will listen a new device event and handle the command queue. Then the request the token with 8 lanes pin code and encrypt command data. Finally, the target vehicle will receive the command and return status. All right, next case is AVIA. The time is not enough, so I will speak faster. If you don't understand, you can ask me later. Controlling a connected car from TSP is common. Then I will show you how to controlling a connected car via AVI. We found a debug port and we get a root shell. Then we got a system file and it's Android system. We have analyzed the system file. Then we found the server of photo platform. You can see the URL at the left picture. By the way, it's HTTP. We got the privileges of the platform by first publishing the malicious app and the system package. The AVI update will verify the signature of the system package, but we get the private certificate already, so we can sign a malicious package with legal certificate and get the privileges of AVI. Generally, the control command sent by the core board is not the raw CAN messages. For Linux, we can find the child devices, name the CAN message at the left, then you can send command by calling write or IO control. Sometimes the instrument cluster display extended by AVI. So you can call in the IO control to write the frame buffer to display anything in this instrument cluster. You know Android is based on Linux because the unsafe development habit. We can access the child device with sandbox privilege. On the other hand, for example, the Android service calling source unverified, and the library can be accessed arbitrarily. We can send a control command with low privilege, but it is not the real CAN messages, it's UART data. The MCU on the button board will pass the UART data following the data format to send the CAN messages. So we can just only send the messages predefined by the automaker. Then what we need to do is to find the control commands so that we can control the car remotely. By hijacking the OTA, we can inject the backdoor code. This code shows calling the service for start air condition. The command you can get by decompiling the APK. We can fetch the UART child device by following the data format. This picture shows the data format we reversed. This head byte is FFA, and the last byte is checksum. Then we got a valid command and send it to child just insert the probe pin into the CAN cable of the IVI. Then 3 bytes corresponding to the CAN message we captured. It can only control the vehicle body, but it can not affect the powertrain. So how to affect the powertrain? I will show you another case of IVI. Connecting our computer into the in-vehicle network CAN bus, when we do some actions such as open door, turn on the air conditioner, it's straightforward to know which command is valid. You can see. In some IVI, we have access to send a raw message to CAN bus. It's not UART data, it's a raw message. The different car has different way. For example, the T-bus using the socket CAN and the serial port in the CAN 0 and the CAN 1. Now let's talk about the attack path. If hackers can get into vehicle manufacturers' intranet, they have the permission to connect with any vehicle in the internet. Then they control one of IVI or T-bus, they can send a CAN bus message into your car. That means that they can control your car remotely. What I share today is controlling a connected car by existing commands. They're enough to attack a lower-end connected car. Actually, how to tamper MCU firmware and bypass the verification mechanism is more challenging. I hope share it to you next time.